Hi and welcome back. We are in the midst of our discussion of buffering and caching in relational database systems, and this is the continuation of this discussion. We will first focus on PostgreSQL and a particular component inside PostgreSQL, the buffer cache, or briefly the buffer, that is used to temporarily hold pages that have been brought in from secondary memory into primary memory. All right, so the buffer is a part of RAM, a part of primary memory that PostgreSQL allocates and uses exclusively to bring in pages from secondary memory that will be used by query operations or by update operations in the near future. Okay, so there is no other way for secondary memory pages, blocks from your SSD or HDD, to enter the PostgreSQL system. Everything has to go through the buffer cache. So this is the only route. So we've got the secondary memory here, a hard disk drive, maybe an SSD, and we want to perform select or update operations on particular tables, so on particular blocks in the heap files of these tables. So we need to bring in the regarding blocks of that heap file, of that table's heap file, into RAM to operate on that. The only way to do this is through the buffer cache. So bring in the page into the buffer cache. This is already a portion of RAM, okay, under the control of PostgreSQL. Now we would be able to perform operations like read and write operations on these pages, maybe changing some of the page contents. From the buffer cache, at some defined point in time, the contents of RAM of that buffer cache will be written back to HDD to make this information persistent. Okay, because everything goes through the buffer cache, a Postgres controlled part of the system, PostgreSQL and the buffer cache can track which pages are currently used, which pages are more used than others, which pages are obsolete now and are not used by any operation inside the database system currently. So PostgreSQL has full control about the contents and about metadata information about the blocks or pages brought into the buffer cache. Okay, so normally what you would have is that this buffer is of course way smaller than the entire RAM. So I'm looking at this particular relationship here. The size of the buffer is probably way smaller than the size of RAM, because we expect other components of our computer system to be busy and to be in need of RAM. So for one, this is the PostgreSQL software, the database system software itself. It has to be held in RAM. So the buffer cache is not available to fill the entire RAM. There will be other processes running concurrently. Currently, this system is super busy with video recording, and of course, all of the other software, all of the other processes will claim their share of RAM, and they have to be accommodated. So we can set some RAM aside for the buffer cache, but probably not all of it. In PostgreSQL, there is a system-controlled variable, a configuration variable called shared buffers that controls that portion of RAM that is being set aside for the buffer cache. It's set to a default of 128 megabytes, which is okay, but a bit unfortunate. Actually, it's a bit small if you concern the actual RAM sizes that are available today in desktop computers or servers, for example. So there's a good common practice and a rule of thumb to maybe set aside 25% of your RAM for the buffer cache. So a significant portion of pages of the HDD can actually be held in the buffer cache and be accessed quickly with much lower latency than accessing the blocks and reading the blocks from HDD. But of course, it depends. If your system is very highly loaded, if there is a lot of processes going on, maybe a web server is running concurrently to your database system, maybe other users are using the system concurrently, then there might not be a chance to set aside 25% of your RAM. But if this is a dedicated database machine that has nothing else to do but to serve the database and to to optimally respond to database operations, then we might even be able to invest more than 25% of the RAM into the shared buffers. By any means, it's a configurable option. So let's look at my current setup here. This is the interactive SQL shell again, running PostgreSQL at the bottom. And let's see what the current value of the shared buffers variable is. It's 128 megabytes. All right. We could now go to the config file, of PostgreSQL, and edit this value, the shared buffers value, and maybe reserve 25% of RAM, which would be 4 gigabytes of RAM for this particular machine. I could do that now, and I would need to edit the PostgreSQL config file. It's not possible to set this config variable using a simple set command, as you may be trying here. You see, I'm trying to set this value to a ridiculously low value of 128 kilobytes. It's actually the minimum value that is allowed in PostgreSQL, but the system refuses to do so. The size of the shared buffer is really something that lies at the very heart. The buffer cache lies at the very heart of the database system. We cannot simply reconfigure it on the fly. We would have to stop the server, edit the configuration file, and restart the server again. We will do this later in the upcoming video when we play with the buffer itself in depth. So be sure to recall that you cannot easily set the shared buffer size using the PostgreSQL shell. Go to the config file, restart the server, and your change of shared buffer size would be respected. All right. As is now common and good use in this course, we will rely on a PostgreSQL extension to have closer looks at the internals of the buffer, of the shared buffer, of the buffer cache. All of these are synonyms for the same thing. There's an extension that I will now enable for this particular, my particular Scratch database. It's the PG_buffer cache extension, which, as you can imagine, would allow us to inspect the current contents of the buffer cache. All right. It already existed, it's now enabled, so please do that on the database that you are using to follow this particular course. There is one thing that's quite interesting. The contents of the buffer cache, is made available to us in terms of PG_buffer cache relation, PG_buffer cache table. So please be aware that internally the buffer cache is not being realized in terms of a regular table. This is just our relational means to inspect the buffer cache with just an array of memory of 128 megabytes currently inside my system. So this is just the externalized one view of the content of the buffer cache. And this table would contain one entry, one row for each page, for each 8 kilobyte block, that is maintained under the control of the buffer cache currently. So 128 megabytes divided by 8 kilobytes, that should be 16384. So I think currently the buffer cache should contain 16384, 16K of pages. And that's what you can see here. The count of pages inside the buffer cache is 16384. This would decrease or increase when you modify the shared buffer's config parameter. Okay. We will, in due course, we will look inside the individual pages that are being held in the buffer cache. All right. So how would the rest of the system, how would PostgreSQL internally talk to that buffer cache? What would be the API, the application programming interface that PostgreSQL internally itself uses to talk to the buffer cache? The API is very narrow, very simple. We need only very few calls, very few methods to talk to the buffer cache. Okay, so when PostgreSQL internal algorithm, for example, the evaluation of a SQL query or a SQL evaluation of a DML, of an update statement, needs to access the pages of a table, then it would go through this particular procedure. It would use this particular skeleton code to get hold of a particular block inside a table to do its operation and then mark the block as being free or being done with. And this procedure would first request from the buffer to read a particular block of a particular table. Hey buffer, we want to access this block of this particular table. Please enable this for me. Read buffer would do its thing internally. We will have a look very brief in a minute, and would then respond with two things: with a memory address M, the memory address at which the next code, the upcoming code in PostgreSQL, will be able to see the 8 kilobytes of memory in which the block contents now live. So reading memory at address M, 8 kilobytes of memory at address M will reveal the contents of the requested page inside the table. Read buffer will also return a buffer page handle B here, which we can use in subsequent API calls to identify this particular block, the particular page that we have mapped into memory, to identify that page to the API and say release that page after we are done with operations on it. Okay, so once we've done the first read buffer operation, we may now access the memory at address M, the 8 kilobytes at address M, and this would be code located here where I've just drawn the line. If that code actually modifies bits in these 8 kilobytes, if I modify the page located at M, if I modify locate page B, then it's my duty as code to indicate that to the buffer and mark that page B as dirty. Okay, so the contents of that page are now differing between the block version on the secondary memory device and the internal version that we have brought into memory. This is called the block is being dirty. Okay. We could go on with our operations here, but at one point we would be done with all the bits on that particular page. So all of our operations are done. Maybe the select or update statement have been processed and completed. We would then indicate to the buffer that we are done with page B and would release that particular page B again. Okay, this is very important because space in the buffer, as we've discussed already, is very precious and very sparse. So indicating to the system that this 8 kilobytes of memory in the buffer are now not needed anymore by this particular process is vital. All right. So what we can see is such bracketing: read buffer and release buffer. That would be a bracket, and actual operation would be occurring inside that bracket. This bracketing is something that you will always see when it comes to the implementation of such database operations. Internally, when the buffer has brought in a particular page from secondary memory, it will not only hold the 8 kilobytes of memory brought in, but it will also hold meta information, information that allows the buffer to decide what kind of page is being held inside RAM currently, how important it is to the rest of the system, how popular it is regarding access to this page, and whether it has been written to, whether it's been dirty or not. Okay, so the buffer is internally realized as an array of RAM, you could say. It's an array of RAM. As I told you, it's not the PG buffer cache table or relation. The buffer cache itself is really an array of buffer pages inside RAM. And each of these buffer pages is associated with meta information in the so-called buffer descriptor. So this would be just an excerpt, just a sketch of what you can actually find in the buffer descriptor. There are many more interesting stuff is to be found in the real system, but for our current discussion, these few bits would already be sufficient. We would find a so-called reference counter for each block B or for each page B. And the reference counter indicates how many internal operations are currently working with page B. It might be more than one operation, more than one select operation, or more than one update operation that is currently inspecting the contents of a particular page B. And actually we hope that this is the case, because bringing in a page that is used more than once means that we have to perform I/O only once, but provided a value to many processes, many select statements, for example, inside the system. And that's a good thing. And the ref count, the reference count of B, indicates that there are a number of processes, a number of operations inside the database system that are currently interested in page B. If that value is 0, nobody is currently interested in this particular page. All right? The higher the number, the more popular it is currently. All right. Okay. So this is synonymous to the number of times that read buffer has been called for this particular block of the inside the buffer. Okay, this ref count, if you're looking at literature out there, at textbooks for example, you will sometimes see the name pin counter for this particular page here, but we will go with ref count in this course. Okay. Usage count is a counter that lets us know how many read-write operations have been currently performed on this block. Okay, so this is how busy the page currently is, and how many bits are actually being investigated on the page. Okay, so that would be the number of processes currently interested in the page, and this is the number of times that the page has actually been accessed. So the higher the usage count, the more busy are the bits on this particular page. And the dirty bit is just the Boolean value indicating whether the bits inside the buffer differ from the bits on the secondary memory, whether the page in the buffer differs from the block on the secondary device. This is vital information when it later comes to releasing and freeing a particular page in the buffer. Okay, so let's have a brief look at how a read buffer routine, the read buffer function inside the PostgreSQL buffer cache API might be implemented. So this is just a sketch of code here, but it could look something like this. Actually, this is a sketch of, or an excerpt of the real code, a sketch of the real code that you would find inside PostgreSQL. So the read buffer call would get two parameters, the table and the block that we are interested in regarding this table. The good case is the case above this dashed line here. And the good case indicates that somebody else has already requested buffer page B, that particular buffer page B, or that particular block of the table from secondary memory before us. Okay, so that block of a particular table has already been requested before. It has already been assigned a buffer page B, and it's already present in RAM. Then there is nothing left for us to do. We don't have to do I/O in particular. All we have to do is that the number of processes, the number of users, database internal users of this particular page B has now increased. And we are immediately ready to return that block handle, the block handle B, to our caller, and the address, the memory address M, where that particular page B currently resides in memory. And our caller could immediately continue its operation and write to the 8 kilobytes that are indicated by this address. The bad case, the case that will be more costly to us and will indeed involve I/O, is below the dashed line. This is called a buffer miss. And in the buffer miss case, nobody has currently requested to operate on this particular block of a table. Its mirror image is not being found inside the buffer cache, the 128 megabytes, for example, that we have set aside for that. So what we are going to do is we will need to bring in that block from secondary memory into the buffer cache. For that, we would need a free place, a free spot in the buffer cache. And it's not a given that such a free buffer page actually exists, because, as we told already, the buffer space is limited. Okay, so let's look for such a next free buffer page, and let's call it V. If there is no such free V, then we need to make some space inside the buffer cache. We would need to identify a page that is currently present in the buffer cache to be the victim, to be the page that has to be written out of the buffer cache and back into secondary RAM, or if we are lucky, a page that we can simply overwrite and forget inside the buffer cache because it has become obsolete. So that's some black art here. Identify the page inside the buffer that is of least value, that will probably not be needed in the near future. No other process is currently relying on the page. It's considered obsolete by now and would be the victim. Okay, so let's just assume that we have an algorithm available that can find the victim for us. We will look closer at how the internals of find victim buffer page may look like. If find victim buffer page can identify such a victim for us, let's call it V, then we would just check whether the victim is indeed dirty, if somebody has written to it. If so, then somebody is relying on the change bits on that page V, and it would be our task now to write the page V back onto its disk block, so that the disk image reflects the contents of the changed buffer cache. Okay, so this would involve some I/O if the page is indeed dirty. If no bit has changed on the victim page, then its mirror image is still the same as in the secondary memory block, and there would be no need to perform I/O at this particular point. So this is actually the value of the dirty bit here. Okay, then, because we haven't brought in that particular block from disk before, we would need to perform the I/O. This is where another I/O operation is needed here. Okay, so after this read operation, that block would be available inside memory. It would be assigned a ref count of 1 now, because we are the only user of this block currently. Nobody else is using this page, and as of this time, it's not dirty. We have just brought in the fresh bits from the secondary memory. Nothing has been changed yet. The block is clean still. And well, this would be the block handle and the address that would return to our caller, now ready to access this new page. So we would have to identify and tell apart the hit, the good case, the very efficient case, no I/O, and the missed case, which even might lead to two I/Os, a writing I/O and a reading I/O, if you're unlucky. Okay, so we have already indicated and discussed what clean versus dirty buffer pages mean. Of course, if I'm doing a read-only operation, a read-only transaction on the pages of my table, then all of these buffer pages will remain clean. A select star operation will normally leave all the buffer pages clean. So, but there's some caveat here that we will discuss in a larger experiment in one of the upcoming videos. So, but normally read-only operations will leave the buffer pages clean, and clean victims need not be replaced as we've just seen in the sketch of the read buffer routine. All right. Of course, it would be our duty as a process inside PostgreSQL to really indicate that we have altered bits on a particular page, and we would use the mark buffer dirty AP call that we have already mentioned. Its internals are super simple. We would just set the dirty bit to true here. All right. There's a background process running inside our database system, the so-called checkpointing process, which would walk the buffer pages, the currently loaded buffer pages, and look for the dirty pages and write these back to secondary memory. This will not happen often because it involves I/O. It could involve heavy I/O if many of the pages inside our buffer cache have been marked dirty. So this is something that can be configured, and you see here in the footnote that there is there's this configuration parameter of PostgreSQL, the checkpoint timeout parameter that says, like every 5 minutes, for example, perform checkpointing and bring the dirty buffer pages in sync with their block contents inside memory. We can also use the explicit checkpoint command to force the syncing of the buffer contents with the actually on disk image. Of course, at the cost of probably lots of I/O. We have seen that when we were talking about the page contents already, when we were using the page inspect and the PG free space extensions. Before in our discussion, we were entering this explicit checkpointing command. So this system is mostly idle, not much checkpointing on dirty pages to write out here. This was quick, but in a heavily loaded system, this might take some time. Okay. So when we have to release a buffer page, this is very important to the system. When we have to release a buffer page, then it's time to decrease its ref counter, because there is now one database process less interest in the contents of page B. Okay. If the ref counter of a particular block B or page B inside the buffer cache is larger than 0, then there is some database operation. There's some database operation inside our system that is currently relying on the bits of that page being available in the buffer cache. Somebody is relying on these bits if the ref counter is larger than 0, and this means that this particular block B or page B inside the buffer cache could never be a victim that is being evicted and then removed from the buffer cache currently. Somebody else would be very disappointed inside our system. So the ref count indicates that currently the page has to remain in buffer until the ref count goes down to 0. This is why this ref count is sometimes also called the pin count, or that a block B with ref count B larger than 0 is called pinned, because it's pinned inside the database buffer. It cannot be removed by any means. All right. So release buffer would be the closing bracket of AP calls that we have mentioned before. It would just decrease the ref count here at this particular point. And as you can see, that's all that is happening here. No I/O is happening. No writing back of the RAM image of the block B back to the secondary memory. And that might be surprising to some of you. And so I invite you to ponder that question and try to understand why a release buffer operation on page B will not write the bits of page B back to the disk, even if the ref count of B is now going down to 0, and even if the page B is now dirty. So, all right, we will come back to this question, but for now, I invite you to think about this for a minute. All right. And this is something that we've already answered and discussed. A pinned page with ref count larger than 0 is just not to be considered a victim, because somebody is relying on this page still. All right, so this would be the very brief, very slim API of the PostgreSQL buffer cache. The read buffer operation, the opening bracket, the release buffer operation, which would be the closing bracket, and the mark buffer dirty operation that indicates whether we have written to the bits of a particular page. This is the API. We will look at this more closely and how all of this is operating internally, and we will have a larger experiment based on our PG buffer cache extension in the next video. All right, looking forward to walk you through this experiment that will, I think, make many of the internals of this buffer cache clearer and answer many of your questions, maybe. See you then. Bye.